Okay. Shall we start, Supratim?
Yeah, let's go ahead.
Yeah, so I'll introduce yourself, myself. I'll talk about Ati Motors. I'll just give a little more introduction about our tuggers, and then I'll give a handover to you.
Sure. Thanks, Shilpa.
Yes. Good morning, everybody. Welcome to our webinar on advanced safety solutions for tuggers. We are delighted to have you all with us today to explore a cutting edge strategies to improve workplace safety and enhance efficiency in material handling. I thank you all in advance for giving us this time. And I am Shilpa Parimi, and I am the lead technical writer at Ati Motors. I work closely with our engineering and product teams to document and communicate the technologies powering our autonomous solutions. It's a pleasure to be your moderator for today's session. A brief introduction about Ati Motors. Ati Motors is a US based robotics company specialized in the design and manufacturing of autonomous and electrical vehicles for industrial material movement. We are headquartered in Detroit, USA, with our excellence center located in Bangalore, India. We have our regional offices in Mexico, India, and Southeast Asia. Our service personnel and partners operate across multiple global locations. Our flagship product line, the Sherpa series, includes a range of autonomous mobile robots, famously called AMRs. From mechanical design to AI driven navigation systems, we build them in house. Our Sherpas are designed to integrate seamlessly into existing workflows, improving productivity with zero infrastructure changes using natural navigation technology. Coming to the context of this webinar, this webinar is a part of ongoing series on knowledge sharing, where we highlight innovations in robots and automation for industrial environments. Through these sessions, we aim to forward expert insights, real world applications, and thoughtful discussions of the future of autonomy. And today's topic is advanced safety solutions for tuggers, focusing on how AMR tugging solutions can boost safety, efficiency, and automation across industries such as automotive and FMCG, etc. We will look into real world case studies from our leading manufacturers and share actionable insights to reflect both engineering and on ground learnings. Today's key speaker is Supradim Mujumdar. He has done his bachelor's from India and master's from Virginia Tech, USA, and he serves as a principal autonomy engineer at Ati Motors, where he leads initiatives in controls, navigation, and perception systems. With extensive experience in developing perception systems for autonomous vehicles, and advanced robotic systems, he's playing a very pivotal role in the evolving of Sherpa series in Ati Motors. Uh, and his guidance from concept through successful deployment of more than 140 units now. It's from bot 0 to bot 140 plus counting. He's with us. It's more than half a decade. He's with Ati Motors, and his expertise centers on seamlessly blending cutting edge algorithms into real world engineering to deliver reliable and robust autonomous solutions. His practical system level perception makes him a perfect person to walk us through today's session. A little housekeeping notes. The session will run for 45 minutes, followed by a 10-minute question and answer session. Please use the question and answers tab in the window to input your questions. We will be taking questions in between the topics, each topic after each topic. So please feel free and submit your questions at any time. And the session is being recorded, and the recording will be shared with all the registrants after the event. Uh, and With that said, Supratim, hi. Uh,
Hi, Shilpa.
Hi. So let me talk about our Sherpas. Can you? Yes. So these are our Tugger lineup today, and this is the Tugger family. Sherpa XT here has the capacity, and we are still striving to make it carry 2 ton plus, and Sherpa XT Lite here carries 1.5 ton, up to 1.5 ton, and Sherpa Pivot is a mini, and it could carry up to 500 kgs. It's a half a ton, to be precise in the tons, and then our Tugger has already been proved a workhorse. So after saying this, I would like to hand over it to our speaker Supratim. Supratim, please carry on.
All right, sure. Yeah, thanks for the colorful introduction, Shilpa. Yeah, you can see the Tugger lineup that we have in production all across the globe. We have about 100 plus tugs, around 10 or so XTs, and a couple of pivots plying in factories and warehouses across the globe. I think there's about 20 or so vehicles in North America right now as we speak. Yeah, it's about 8:30 p.m. in India right now. So good evening to folks joining from India, and a very good morning to folks in North America. So I'm gonna start off with a bit of a summary of some of the previous sessions that we've had. We've had a couple of sessions on sensors, or the sensor suite that we use on our robots, and a little bit of autonomy, just so that you're familiar with the lingo and the concepts that we use to describe how our robot moves, right? So in figure one, you see the XT, which is the 2-ton tugger, with quite a few sensors that we use to perceive the world around the vehicle. Right in the on top of the vehicle is a 32 beam lidar. And that is the main sensor that we use for localization, for perception, for any of the fancy algorithms that you're going to see later on in the talk. It gives you a 360-degree view of the surroundings, and that is what we use for things like object detection, for localization, for seeing if it is safe to go around a corner with a trolley. But there's an issue with the LiDAR, being that it cannot really see stuff very close to the ground for about a 2 meter radius. You can see that in figure number two, where the LiDAR field of view is great further away from the vehicle or the Sherpa, but you see a circle around the vehicle, and that is the blind spot of the LiDAR. Now, to cover up that spot, you have a camera placed at 38 centimeters from the ground. You can see in figure number one, which covers up that blind spot. That, of course, helps when you're going forward. But if there are obstacles right next to the vehicle, or obstacles that the trolley may hit, you want sensors to the sides, and that's what the ultrasonic sensors do. So it's a combination of these sensors that we use to ensure safety, not only around the robot, but around the trolley as well. And this is the stuff that we do with all these sensors. We move autonomously. We are practically self-driving cars, but in industrial settings. What do we need to do to drive autonomously? There are three fundamental questions that we need to answer, right? The first question is, where are we? So in column number one, we are trying to localize. So you have a vehicle with a LiDAR, you go around and you build a map of the place. So you can see that there is a nice 3D map of LiDAR point clouds that we construct a map with. And then once we are on the site, we get a live LiDAR frame, and we localize on top of that map. That's kind of what you do when you pull out a map, or what you do on Google Maps. You know your surroundings, and you kind of figure out where you are based on the sensors that you have. So now we know where we are. Now we need to perceive what is around us, right? So that's the second question. So you can see that we use the camera to see that there is a pillar in front, there's another robot to the right, but of course that is in RGB, which is what humans perceive. What you see in the column in below is what the vehicle actually uses to infer objects around itself. So you can see there's a bit of purple, which are basically the ground points. You can see that the robot on the right of the camera frame has been segmented as a separate set of points, and everything in the background is in red. So we know what is around us, we know how close things are around us, and that's what we can use to answer the third question, which is where do we go and how do we get there? So we know where we are, we know what's around us, we need to do some path planning. So we plan a path around obstacles. We, of course, need to execute the tasks that the robot needs to perform to get material moved around a factory or a warehouse. So you can call that a mission if you'd like. So the robot has a route that it needs to track, and along the route, if it encounters any obstacles, it will first detect it and stop, because safety first. And if possible, if feasible, it would try to get around that obstacle and plan itself around, right? So that's the basics of autonomy right there. Any questions so far?
No, Supratim. There are
Yeah.
no questions. So
Perfect.
basically, you have been showing us the heat maps, and you have a structured way of telling how does the tugger, I mean, how does the AMR know where it is, where it
Yeah.
has to go,
Yeah. So this is
and
basically a sneak peek into the brain of the AMR. This is what the
eh,
vehicle is actually seeing. Um,
exactly.
and if you look at the path planning and control column, the vehicle itself is this pink color box or pink color
Yeah.
rectangle. The lidar points are in blue and red, so you can see a lot of shelves in red. You can see that there is a red in the path that the vehicle is trying to track, which is the dotted lines. So that's the mission that the vehicle is trying to execute. And you can see in the last plot that there is, it looks like a human being to me, standing in the path of the vehicle. And you can see a circle suggesting that we have detected that obstacle and we are going to safely navigate around it.
Okay. You have more live examples and solved problems to show us as an examples
Yeah.
further, right?
Yeah, yeah. You'll
Yeah.
get
Yeah.
familiar with these plots as we go through some of the algorithms that we have on show.
Yeah. That would be
Okay.
wonderful.
Yeah.
Yeah.
All right. So now to the heart of the matter. The reason we're talking about tuggers is because of the stuff that they're tugging, and those are trolleys, and trolleys are tough. They provide so many problems to us as dev engineers. They are There are a wide variety of trolleys that I have come across in my 7.5 years at Ati Motors. No two sites or no two customers really have the same trolley, so you always have to kind of be on your toes with regard to that. They come in different form factors, different sizes, different configurations, different numbers. So you can see in figure number one that the vehicle is pulling one trolley. Sorry, it's a single vehicle in red, pulling three trolleys, in fact. And you can
Yes.
see the complex nature of the paths that the trolley take with respect to the vehicle. You can see that the first trolley, the second trolley, and the third trolley have been pushed off from the actual path that the vehicle intends to take. And
I,
in the second video, can anyone guess how many trolleys there are on the vehicle? So the vehicle is in pink.
and it is moving. I think we do not have that chat option here. I'm not sure.
Yeah.
So, but it looks like
Yeah. So I can
there
see,
is a, yeah.
yeah, the first couple of trolleys, maybe as you get further away from the vehicle, the LiDAR, of course, is occluded by the trolleys themselves. So now I cannot even see anything beyond, let's say, the third or fourth trolley. So let me try
Yeah.
to play the video back again.
Somebody already answered it as four trolleys
Four.
probably.
Yeah, four are clearly visible,
Visible, yes.
but that's not the right answer. There are actually 12 trolleys in fact. So it's two rows of six trolleys. So there are two hitches on the vehicle.
Uh,
And
so
right when it
yes, somebody
turns, yeah, right
also
when it
answered it as six.
yeah, so right when it turns, you
Right.
can kind of see that there are two trains of trolleys attached to the single robot. And that's a
Yes.
challenge. So you need to account for the sweep of the trolleys as it makes the turn. It's very difficult to detect, of course. And with 12 trolleys, they're going to be kind of hitting each other. They're going to deviate from the path. And that's a challenge. And that's what we're trying to solve right now. right? And another challenge with trolleys is that um, they carry, let me just mute that. They carry the payload that we are tugging. So the 1.5 tons or the 2 tons that we spoke about in the tugger spec sheet is all on the trolley. And how you distribute that weight really affects the dynamics of the system. So here, this is like a toy example. The person over here has placed 60% of the payload at the rear end of the trolley, and that causes a lot of instability. So as a thumb rule, you would like to place the payload in the front. So now you have 60% in the front, and you can see the same force that the person induces on the trolley system now is stable. And now he's going to make the system unstable all over again. And these are the challenges that we face on a day-to-day basis, and we're trying to solve. And these are honestly quite tough problems. Like I said, no two sites are the same, no two trolleys are the same. So we really need to be on our toes with regard to our solutions.
So basically, the example you have shown is it's a walking track. I mean, the treadmill.
It's a
It's a
treadmill.
treadmill, and the
Yeah,
car and the toy car is placed along with its trolley.
yeah,
Now the red weight is placed behind, so there is the movement, the snaking effect is more, and
yeah,
when the weight distribution is corrected to the front,
yeah,
then the snaking issue has reduced.
yeah, yeah.
So even the weight distribution on the trolleys also play a very important role.
Yeah, so what this is
The
describing
safety.
is the natural dynamics of the system. Of course, we have motors ourselves. So now the trick is how do we control an unstable system or an oscillatory system with the actuators that we have. But of course, as a thumb rule, if our customers follow these 60-40 rules for weight distribution, that itself makes the system inherently stable.
But then we still have to navigate the other 40% of it, right?
I mean, yeah, basically, once the system is stable, it's easier for us to control the vehicle.
Yeah.
Yeah, yeah. Okay. So we're going to talk about some of these solutions that we're developing and have developed in the last year or so to address some of these problems. And the first problem is in order to do something about the trolley, we need to detect the trolley itself. So one solution that we have developed is using the LiDAR, the vehicle's main sensor, to detect the trolleys. So what we do is of course, the LiDAR is a 360-degree sensor, so it can look behind the vehicle when the trolley is attached, and you get point cloud data of the trolley. And you can see in figure one that the trolley has a nice distinct little mask, if you want to call it that, or a signature, which doesn't really change over time, right? So we can kind of try to find the LiDAR points behind the vehicle that match that mask, right? So that's what we're doing in figure number two. We're kind of perturbing the mask that we have, and we're saying, hey, I'm getting most of my LiDAR point hits at 0 degrees, and therefore the trolley must be there. And as the vehicle moves on, you kind of keep doing this scan match. That's what we call it in autonomy terms. And you keep updating the scan as you get LiDAR point hits. And that's what's happening in the video in figure number three. So you can see that the vehicle is moving. That's in the center of the LiDAR frame at 0, 0. And the first trolley is detected pretty well. But you can see as the vehicle passes through the corners, the second trolley and the third trolley are not really all that clear. The pillars kind of obscure the LiDAR. Right now, when the trolleys are all in line with each other, it's difficult to see the body of the trolley. What we're doing to kind of filter out this sort of noise in the system is to use a Kalman filter to kind of make sure that we are robust to these occlusions and the movement that the trolley may have or the noise from the sensor itself. It does a fairly decent job of detecting the first trolley, but the second and third trolley are still a bit difficult right now. And that's why we kind of wanted to see if there's an alternative approach to this, which is basically using machine learning or neural nets. So that's what we're doing here. Instead of doing a 2D LiDAR frame scan, we are doing the detection in 3D. right? So now you have a 3D view of the LiDAR, and you can see that the trolley is a little more richer in terms of LiDAR points. And what we're also able to do along with this is, since it's in 3D, it's very easy to detect a torso of a human being walking next to the vehicle. And that allows us to be a little bit more safe when there's a human in the vicinity of the vehicle. So now not only are you detecting the trolley, but you're also detecting the danger around the trolley, and that helps a lot, right? So basically, you're not only working with tiny bits of point cloud data, but you're also working with semantics. Now you have a nice big cluster that says trolley, and you have a nice big cluster that says human. That is very rich in information, and that opens up a lot more possibilities for us, right? So any questions right now?
Not yet.
All
Uh,
right.
gu- yeah, so I request everyone, if you do have questions, please use the question and answer option and do type in your questions. We will be answering it in between. After every topic is over, we will actually give a gap of a minute and then we will go ahead.
Okay.
Currently there are no questions, we'll go ahead. Yeah.
Yeah. All right. So this is the same thing in a top-down view. So this neural net uses a convolutional neural net. It's based off of something called point pillar. So we use these point pillars as kind of like the input to the CNN, and it segments trolleys and humans and other objects like carts, common objects that you would find in manufacturing or warehousing. So this is pretty cool stuff. Um, and of course, now that we have detected where the trolley is, now we can start with our path planning and actually make the vehicle safer in terms of its routing. And the first step is, of course, if you know where the trolley is, you know where the trolley is going to be in the future. So in figure one, we are doing that. So you can see the trolley in the yellow colored boxes behind the vehicle. The vehicle is always going to be in pink. And you can see that the vehicle's padding is fairly small, or it's narrower than the trolley. And you can see the circle over there highlighting an impending collision that's not colliding with the vehicle, but it's actually colliding with the trolley. So we have detected that and we have stopped. And of course, stopping ensures safety, but we want to take it a step further, and we actually want to navigate around these obstacles as well. And that's what we're going to talk about in the next coming slides, where we actually do obstacle avoidance around objects that may be in the path. So this is a paper by Sebastian Thrun and team from way back in the day, I think 2010 or so. He was a part of the original Stanford DARPA projects and is kind of like a pioneer in path planning and control. So this is a Frenet frame path planner, and you can see the scar in the middle. Let me just replay that again. It's able to navigate around all the obstacles in a highway-like simulation, and we're trying to do the same. Of course, this doesn't have a trolley attached, so that adds another layer of complexity for us. But yeah, we have developed some algorithms that take the trolley into account when we do avoidance, and we're going to talk about that next. Right. So yeah, obstacle avoidance is it's fairly commonplace these days in robotics. Robots usually have predetermined paths or missions between where they pick up material and drop material, and obviously they would like to stick to these predetermined paths. But if there is an obstacle that it can safely navigate around, they tend to do so. Of course, we need to do it with the trolley behind. And that's what you see in the video on the right. The vehicle was going on the straight line path, but then it had to avoid, I think, a human standing along the path, and it rejoins the path as soon as it's free to do so. So that's the basics of obstacle avoidance. And as I'd mentioned with Sebastian Thrun's paper, we do this using something called the Frenet space. And what that is basically we're working in a different frame of reference, or a different frame altogether. So in the world that humans live in, we kind of like to think as things in Cartesian coordinate frame systems, right? So you have an X, Y, Z, whatever, to describe the location of a particular object in the space around you. The Frenet frame is different. The Frenet frame lives along the arc length of a curve. So as you can see in figure number one, what is a curve in the Cartesian space is now a straight line. in the frene frame, and that is beautiful. That's an engineer's dream, because that makes our job so much easier. So path planning around a curve can get very complex, but for me to path plan to do path planning in a straight line is quite simple. It's kind of like, if you've seen an like Usain Bolt running a race in the Olympics, right? They have different lanes, all parallel to each other. Even in the 400 meters, there's a nice circular set of lanes that all the runners adhere to. And that's kind of what we're trying to take advantage of in the Frene space, where everything is a parallel line. So if you look at figure number 2, what is a curve in the Cartesian coordinate frame is now a straight line, and then it is easy to make um, alternative candidate paths for the vehicle to use to navigate around objects. So if there is an object to the left of the vehicle, it is going to pick a feasible path to the right of the object, right? And that is so much easier in the Frene space, where basically we're just dealing with lines, which are very computationally efficient, and geometrically as well. It's a lot easier for us to visualize. So you're going to see some examples of the Frene candidate paths. So you can see that the vehicle is going to maneuver itself around the blue color box and the cardboard placed in its path. And as soon as it's safe to do so, it is going to rejoin the original path. Yeah, so it's coming back to the original path right now. Yeah, so you can see the candidate paths in the first figure over here. It's always looking for objects, and as soon as it finds that there's an object colliding with one of the paths, it is going to pick the most feasible candidate that is collision free. And of course, you need to take into account the trolley. Oops, let me just go back there. And yeah, so it's always looking not only for collisions with itself, but for the trolley as well. So it's always making sure that the trolley train or the entire system of the vehicle plus trolley is collision free.
Right.
All right, so any questions with the Frene space avoidance?
There are none yet.
All right,
I
let's,
think they're saving it for the last
all right, yeah,
case.
we'll have a nice Q&A later on. All right, so we're gonna move on. Yeah. So another solution that we have to improve safety across factories is ATI. And it's not always going to be possible for the vehicle to navigate around objects, especially if there are other robots that it is sharing the warehouse or this manufacturing facility with. So ATI is a solution where we plant a camera in important intersections. So for example, here it's a T junction, and the Ati Sherpa is basically unaware of the other robot approaching from the other lane. But if you do prop up a camera at this intersection, it can detect a robot for you, and it can tell the Ati Sherpa to stop and give way to the other robot. So you can see this red color box, which is the area of interest. That's kind of where we want to make sure that the robot does not enter unless it is absolutely safe to do so. So now you're basically making sure that the robot only enters with its trolleys attached when it is absolutely safe to do so. So this is something that we hope to deploy very soon. All right. Another thing you can do once you have trolley detection in the loop is to also park a trolley backwards. So the vehicle here again is in pink, and there is an orange colored trolley that it is parking in reverse into a parking bay. And that is only possible if you can detect the trolley using either the AI method or the LiDAR based method. It is often difficult to instrument trolleys. That's a question I get asked often. Why not just slap on like an encoder or something else to the trolley? Customers have hundreds of trolleys at their site, so it's going to be near impossible to instrument all 100 trolleys. And the conditions in factories are really not conducive to instrumenting, these very delicate sensors on something that is going to be lifting, 1 ton and above. So we think that a sensor-based solution is really the way to go for this. All right. And another thing is, we do focus on safety and making sure that we are absolutely collision free. But the world is not perfect and accidents do happen, and we want to make sure that we do not um, aggravate any collisions that may happen. So this is an IMU and current based solution that we have. So in the case that some object or a human does get stuck either on the vehicle or on the trolley, we do not proceed any further. The vehicle stops almost immediately. Right, so here somebody's going to wedge the box in between the vehicle and the trolley, and we sense the spike in current as a result of this collision, and we stop. So that's another safety solution that we have in the pipeline. All right. So yeah, these are some of the solutions that we have. Of course, they come with challenges. We saw that the trolley dynamics are difficult to deal with. Occlusion near the trolley and the environment around the vehicle makes it very difficult to use the LiDAR to detect trolleys. Trolleys come in various shapes and sizes, and therefore they may be very difficult to debug. And in some cases, you just need to plant extra sensors, like we saw in ATI, where you have cameras mounted at critical junctions in factories, and we can use those to improve safety. That being said, there are some interesting solutions that we have been dabbling with in the past few months, which are looking to address even these challenges. One thing is, of course, like I said, it's difficult to account for the wide array of trolleys that we face on a day-to-day basis. So it's nice to have a simulator environment. This is NVIDIA's Isaac Sim. So we use this to simulate trolleys, design different types of trolleys that we use for detection and obstacle avoidance. So it really helps to have this environment. If you look closely, you can kind of see the caster wheel of the trolley is kind of swiveling around. So it has physical or physics realism as well. And that's great to have. Right. So, and another solution that we're working on with a partner company. The company is called AutoInfer. They're also Bangalore based. You can look them up on LinkedIn. Is mounting a camera to look behind the vehicle and detect trolleys. So we're trying to bridge the gap that the lidars cannot really cover. So we're going to place a camera on top of the vehicle facing backwards, and as you can see, it has a nice top view of the trolleys, even as the trolleys go around a corner. And we think that that may be a feasible solution going forward, in addition to the LiDAR, of course.
So this is an added measure where we know that the trolleys are going to be taking a very heighted level of loads, and then we place the camera strategically to get the
Yeah.
view. Okay.
Yeah. And for example, the first trolley may be completely opaque. It may be filled with boxes, and therefore you may not be able to see the second or third trolley. So mounting the camera at this height with the FOV that the camera has, you should be able to detect all three. I mean, you can at least see the tops of all three trolleys in this particular case.
Right.
Yeah.
We will have that angle perception and everything where the trolley is
Yeah. So
moving
basically, you're
itself.
just adding more sensors to the array of sensors that we have already, and that should fill in most gaps.
Okay.
Yeah.
So we are trying all the 360 degrees up, down, in all the angles by strategically
Yeah.
placing all the sensors. They're
Yeah.
internal, external, whatever it is, we get the sense of the obstacle and then we are safe.
Yeah. And the added
We,
benefit of having a camera here is that you can also detect a human approaching the trolleys. So you need not really depend on the current sensor or the IMU spikes to detect that the human is stuck. You can probably stop the vehicle right before the human even gets a chance to get stuck between these trolleys.
there is a question on what are all the types of objects that are detectable.
Mhm.
So objects and obstacles that are detectable.
That's a good
You ready?
question. Yeah, that's a great question. So if you look at some of the traditional training data sets, like the Kitty data set, that is famously used worldwide, they largely are trained on data that is collected from outdoors. So you have cars, trucks, bicycles, humans, dogs, trees, road signs, curbs, etc., which are easy to detect. So these algorithms, at least for vision systems, are very well trained. I don't know if there are any solutions that are ready made right out of the box that can detect things like trolleys. or small boxes in warehouses or machinery, or even point cloud data for that matter. I did mention point pillar. So point pillar is trained off of lidar data as opposed to cameras. But again, that is trained on more traditional objects like carts, um, vehicles, humans, like we saw in the human detection. So that's a challenge.
Yes.
We often need to train these networks again on stuff that is of interest to us. So machinery, um, cardboard boxes, plastic boxes that are used in factories, pallets, stuff like that.
Yes, and then how can safety culture be strengthened? I think I will save this question for the
Yeah,
last.
we
We
can have
will
a
go
nice
ahead.
Q&A later on. Yeah, so I
Yes,
just have a
yes.
couple more slides and then we can get talking.
Sure, sure. Yeah.
Right. So another thing that is very interesting for us to take into account in the, especially in the obstacle avoidance algorithm, is knowing what is static versus dynamic or moving versus static. So this is a object segmentation algorithm. This is something from Cyril Stackness, who I think is in Delft or I think Zurich. Pardon me. He's again a pioneer in controls and path planning. So here you can see that there are, let me just play that again. Yeah, so there are some humans that are walking near the robot, and as soon as they're moving, they are segmented in red. And that signifies that they are dynamic. Now, that's a lot of information again. You can probably plan better around static objects than moving objects. For example, it's easier for a human driver to move around a trash can that is spilled over to on the side of the road as opposed to a cyclist that is pedaling along with you on the road. You would probably want to slow down if there is a moving object around you instead of trying to avoid around them. So that's information that we definitely would like to use for object avoidance.
Yes, definitely. Because the trash can and all are unmovable objects, but then a person who is there, his
Yeah, so,
perception is
so
different. He may move, he may not move.
exactly.
The
So it's unpredictable, right? So you'd probably
Yes,
want to
yes.
err on the side of caution and probably slow down. Of course, in India, we have a tendency to speed up when you see something moving towards you, rather than slowing down.
Instead of slowing down,
Um,
yes.
but yeah, for robots, yeah, we want to make sure that safety is first. So the robot would, especially with the trolleys that it's pulling, you'd probably be better off slowing down when there's a human
S-
walking in front of
yeah, so basically our AMRs, when they are actually used in environments where all the people around are also
you.
acknowledged and knowledged about this,
Yeah,
and probably they also follow all the safety rules
exactly.
that they
Yeah.
have to, and then we can 100% avoid it with the help of this,
Yeah,
right?
yeah. So safety is always first. So especially with human beings working in factories, operating machines around, especially in factories where it's very noisy, you may have earmuffs, you may have gloves, you may not have the dexterity that you may have, you may not have the perception that you may have walking down a street under normal circumstances. So we want to make sure that we give the human the benefit of the doubt.
Right.
Yeah. And this is another really cool path planning algorithm. Let me just play that in 2x. It's a little bit slow. So this is, oops, let me just go back again. Let's play that. Let's make sure it's in 2x. Yeah, so this is an algorithm which is aiming to do dynamic path planning for like an 18-wheeler truck. So you can see that the trolley on the vehicle is massive. It's almost twice the length of the vehicle, and it is able to park itself into the bay. So now you have a different starting position, and it's basically dynamically, it's just iteratively kind of trying to find the most feasible path into the parking bay. And this is something that we can use in factories to kind of bridge that final mile between the material that is there in the trolley and the assembly line, for example, that uses the material for producing a product. We can park it directly into the conveyor line or the assembly line. That way, you don't need a human to kind of take stuff off and lift heavy payloads. The robot can do it itself. So now this robot's gonna maneuver
From all
the
different
trolley. Yeah,
directions to
it's
that
gonna,
parking
yeah,
space.
yeah, it's gonna make sure that the orientation is also maintained when it parks, all in this tight space.
Yes.
Yeah.
So we now can even park with the trolleys double the size of the vehicle
Yeah,
safely
yeah. I mean,
without
if an
actually
18-wheeler can do
disconnecting,
it,
connecting it
yeah,
again. Yes.
if an 18-wheeler semi-truck can do it, then our robot should be able to do it.
Yes.
Yeah, and yeah, this is, I think, the last quirky solution that we have. Let's let the robot figure it itself out, because that's what we do when we first learn to drive, right? We figure out how to maneuver around our neighborhoods. We learn how to drive faster as we get more comfortable in the car, and that's what we think the robot should do as well. So you can see that in the first iteration, the robot was going fairly slowly, and it's still a little bit iffy about what path to take around this track. And as it keeps learning, the time reduces, so it's able to pick up speed. It's also able to take a more optimal path around the track. It's kind of like an F1 track, a Formula One track, where there is the most optimal racing line that a robot or a vehicle can take around a path to make sure that it's got the quickest lap time. So now it's learned over 33 laps, and it's more than halved its lap time. So it's zipping away quite fast. Yeah, and then
Yeah.
it's
So the
gaining
so the
time.
time taken after learning has reduced
Yeah.
drastically to six
Yeah,
point
and
one
and and what and
seconds.
what we think is that the robot obviously is going to learn about itself, so it's going to learn about the dynamics. It's going to learn about the environment around it, so the track conditions or the surface conditions, and it's also going to learn about the trolley that's attached to it. So as long as you're always optimizing over that, you can pretty much tackle any environment, be it snow or ice or rain in India during the monsoons. You're going to be able to
There were
navigate through
such
various
questions actually regarding
environments.
the water and all. Yes.
Yeah, yeah. All right. So yeah, the floor is open to questions.
So
Um,
basically, there were questions, and then you have answered it and covered it through, very, very tactically and all. So they were asking about the types of materials that it could detect. Then the next question was whether it could detect water, oil spillages, etc., in the factory floors, and all that. The next, I think
mhm.
you have answered that in the last.
Yeah,
Yes,
I
our
mean, a lot
AMRs.
of neural nets can detect things like road surface, like textures and stuff like that. I'm sure you can use the reflectivity of water in smooth surfaces, at least, because most factories have smooth surfaces. But I don't think water really is a problem. Oil slicks can be a problem, that I do agree. But I think there are some very basic neural nets like YOLO, which should be able to handle stuff like that. The LiDAR, of course, will not be able to pick up water. It's just too fine a film on top of a surface to be picked up by the LiDAR. But yeah, I do believe that there are some computer vision solutions. And I think we have tried this because we have robots that run outdoors, and at least from a vision perspective, I don't think rain is too much of a problem. It doesn't cause too much of occlusion. Mud is going to be an issue because if the camera is blinded, then of course you can't see anything. So yeah,
There are this type of questions, the mud, the dust and all. Yes, the maintenance part of the AMR is also equally important along with the
absolutely,
safety.
yeah, yeah.
Yes. And how do you balance the cost of safety technology with the long term value it brings to your organization?
Yeah, so I mean, so what's happening is the ecosystem around autonomous vehicles and autonomous robots are, I mean, it's just growing exponentially as the years go by. I mean, some of the algorithms that we saw are fairly recent. They're like 2010s plus, and that's considered ancient in the world of robotics. So as the sensors get cheaper, as the algorithms get more efficient, you're not going to need to spend a lot on these. You're not going to need large sensors. The sensors are getting smaller as well. And it's just going to get ubiquitous. I mean, 20 years ago, mobile phones weren't even a thing, and now everyone has them. So we see that AMRs and autonomous vehicles are going to follow the same trajectory.
And a similar thing is, what measurable benefits have companies seen after integrating advanced safety solutions for tuggers?
Yeah, I mean, yeah, some of these solutions just speak for themselves. Obstacle avoidance is obviously going to help with takt times for the missions that the robots have. So you don't want a robot waiting for a little box that is placed in the middle of the road. You want it to be able to navigate around and make sure that it delivers the material in time. And I mean, it's always paramount that safety is first. So, I mean, I mean, you don't want any damage to materials either on the trolley or otherwise. So yeah, these algorithms will obviously have a return on investment as time progresses.
Yes. And what future trends in safety technology should companies be preparing for in tugger operation?
I mean, the biggest elephant in the room these days is AI, and you have to take AI with a pinch of salt or with a spoonful of salt. That is why you want to mesh AI techniques with traditional approaches, like what we saw with the Frene space avoidance, some of the segmentation algorithms from Throon's lab, some of the traditional path planning algorithms. You want to make sure that you use AI for a very focused problem, and you put that into a larger classical approach, which guarantees observability, it guarantees robustness and predictability. So that you don't leave everything to AI. I think that is what we really need to digest at this moment in this AI crazy world where GPT and Claude and everything is at your fingertips. You really need to make sure that you double down on making sure that whatever the output of the AI is accountable in some other form.
And the same type of question I have: how do cutting edge technologies like sensors and automation enhance safety for tugger operators and pedestrians in busy facilities?
Yeah, I
I
think
think
yeah, human tracking really helps with that, and basically you want the robots to behave in a manner that is safe and confidence inspiring for human beings. You don't want a human operator to be very wary when they're going about their daily tasks. You want them to rest assured that the robots will behave in a predictable and safe manner. So we just want to create that safe working environment for people in manufacturing. And we want to make sure that robots are as ubiquitous as other machinery or other vehicles that we face in day-to-day lives.
what other uh, aspects or softwares also help in achieving the lower ground time?
Um,
Do
yeah, so things like basically being able to navigate. I think it's a navigation question that you're talking about when it comes to optimality and takt time. So yeah, I mean these algorithms, of course, are maturing day by day. Compute is also a factor. It's a dependency. So unless you have the CPUs to churn out these algorithms outputs, you're really not going to get anywhere. So yeah, it's just about this entire ecosystem kind of developing over the years, and it's happening at a breakneck pace. So yeah, we're banking on that.
Okay, then that is all the questions I have.
All right. Yeah,
Yes,
thanks
we
for
have.
joining. We hope to have more tech talks, other talks about the vehicles, maybe some case studies of some of our customers in the future. So, yeah, thanks for tuning in.
Do post us your questions. Even after the webinar, we are ready to answer all the queries. Please contact Ati Motors, and please visit our website to know more. And today, Suprotim have covered a lot of information. It has been a really good 40 minutes, 45, sorry, it's almost 50 minutes of very informative webinar. This is, we had the insights and first hand case studies from you. That is really great, Supratim. Thank you very much for putting all these case studies in front of us. and you have actually given a very easy flow. You have covered the static obstacles, you have covered the dynamic obstacles, and the perception, how, where, when, etc. So I think this is the most common way we have to question and find solutions to the safety of not only AMRs but the tuggers. And we have been futuristic in our using our sensors, our computes, our everything. So yeah, we can end it for now,
All right.
because yeah, we have
Thanks. It's
covered
always
it all.
fun talking about robots. See you next time.
Yes, yes, see you next time. Thank you everybody, thank you for your time.